Hello everyone, I'm Chong, and I will give a presentation entitled Significant Diurnal Warming Events and Ocean Warm Skin Signals Observed by Saildrone at High Latitudes. Due to the time limitation, if you'd like to find further details, you can check the two published papers given below. In a joint NOAA-NASA deployment, the 2019 Arctic cruises consisted of 6 Saildrones departing from Dutch Harbor, Alaska. Saildrone is an advanced autonomous surface vehicle carrying a suite of scientific oceanic and meteorological instruments. Here, measurements from two of the Saildrones 1036 and 1037, funded by NASA, are used for studying the diurnal warming in ocean warm skins at high latitudes. The navigation routes are shown in figure on the left, and the instrument configuration of these two Saildrones is illustrated in figure on the right. The datasets include SST data and also some meteorological variables from Saildrone, and also the downward long-wave radiation from ERA5. Here are some formulae for calculation. As shown in the figure, SST is not a unique definition of the surface ocean temperature due to the complicated and variable vertical thermal structure in the uppermost ocean. There is nearly always a thermally stratified thin layer, commonly known as a cool-skin layer, resulting in a cooler skin SST compared to the subskin SST. In the mixed layer, which is below the skin layer, turbulence tends to cause turbulent mixing, resulting in very small vertical temperature gradients and the strong winds given as the profile in red. Nevertheless, thermal stratification can be sustained by insolation and light winds during the day in black profile, and this diurnal warming has been studied for several decades. Here are the results. To assess the magnitude of diurnal warming, the cool skin effect has been determined with a simple model in dependence on the wind speed first. In the left figure, the fitted curve shows remarkable agreement with some previous results, except for low wind speed below 3 meters per second. Some significant diurnal warming events were observed by two Saildrones in the red plot. Those were identified when the warming amplitudes greater than 2K lasted for at least 1 hour. The large warming events were as a result of strong solar radiation and little near-surface mixing due to low wind speeds. Furthermore, some diurnal warming persisted from one day into the next, on June 15 to 16 and July 8 to 9, due to the midnight sun in the Arctic. Here are two cases examined to show the characteristics of upper ocean thermal stratifications and air-sea interaction. The left figure shows the diurnal warming that occurred on May 19 in 2019, observed by Saildrone 1036, with the largest measured warming amplitude of 5K. At low temperatures, the seawater density depends much more on salinity rather than temperature. Therefore, stabilizing effect of heating is not so important as stabilizing effect of fresh water. Figure D shows the Saildrone onboard cameras recorded a precipitation event in the local area on May 18th. The rain will have lowered the salinity of a thin layer at the surface ocean, where the absorption of shortwave radiation increased and the heat was trapped, causing strong warming signals within the skin layer but a delayed and much weaker response in the water beneath. Figure on the right shows another significant diurnal warming on June 15 to 16, observed by Saildrone 1036 as well, with a peak of 5.1 K. Different from May 19th, the 2-meter air temperature was higher than subsurface SSTs for most of the time, even higher than the skin SST at some times. Such warm air originated from the low atmosphere over the Arctic Ocean but was heated by its passage over land, leading to low surface turbulent heat loss in Figure C. which contributed to sustaining the diurnal warming into the next day. Figure D indicates the warming event occurred close to marginal ice zone, where a less salty surface layer was likely created by melting sea ice, providing favorable conditions for the formation of upper ocean stratification. Theoretically, the Euro-cool skin can be converted to warm skin by reversing the sign of Qc, so the net heat flux is from atmosphere to ocean. Here we focus on measurements from 1036 and we define heat fluxes to be positive downward. Figure E demonstrates positive Qc is concentrated at high latitudes above 60 °N, with magnitudes even reaching 100 watts per square meter. After careful area budget analysis, we select 17.85 watts per square meter as the threshold for Qc, significantly greater than zero, mostly because of the inaccuracy of ERA5 data. As shown in Figure F, the average skin effect is 0.18 K in conditions of significantly positive Qc, with over 96% being positive values, some even up to 0.5 K, indicating the existence of warm skin. Figure A shows the warm skin is observed when air-sea temperature difference is positive, associated with sensible heat indicating heat flow from the atmosphere. Figure B shows that very humid surface air resulting in significantly positive latent heat also contributes to the existence of a warm skin. For most cases, the relative humidity is greater than 99%. Figure C shows there is no obvious dependence of warm skin effect on 10-meter wind speed in this study, as the peak between 8 and 10 meters per second is dominated by the uneven distribution of air-sea temperature difference. While strong winds can generate large sensible and latent heat fluxes, they can also prevent the establishment of large temperature changes across warm skin layers by thinning the viscous sublayer by turbulent mixing. Figure D indicates the warm skins mostly occur under cloudy skies, leading to increased downward long-wave radiation and much reduced net long-wave heat loss from ocean, or even net radiative forcing from the atmosphere. Overall, each component of Qc contributes to the formation of warm skin, and the combined effect is in Figure E. Here, since all the warm skin signals were found during the daytime due to the midnight sun in the Arctic summer, the solar heating effect in the skin layer must be considered. Figure F indicates the incident solar radiation at the sea surface is generally below 100 watts per square meter due to the sun being obscured by clouds. Therefore, as shown in Figure G, the solar absorption in the skin layer is typically below 20 watts per square meter, and the skin effect does not exhibit explicit dependence on the absorbed insolation when it is below 10 watts per square meter. While the absorption of solar radiation in the thermal skin layer contributes to the formation of a warm skin, it is not the dominant cause of the temperature difference across the sublayer, as the water beneath is also heated by the solar absorption. Figure H further demonstrates that the turbulent fluxes are the dominant component, and the fraction of solar absorption in the total heat flux budget is usually less than 30% when the four components are all positive. Here are some take-home points, and generally speaking, those significant diurnal warming events and ocean warm skin signals are rarely reported in previous studies. For the future work, it is necessary to improve the model schemes for diurnal warming applied at high latitudes and establish the model schemes for the warm skin. Also, the mechanism of warm skin should be further investigated. And that's my presentation. Thank you for your listening.